I think we have already mentioned MJO several times in the context of the cyclogenesis. Here we will just add a couple of more details to the MJO and cyclogenesis. This is a nice animation because it shows here the phases of MJO propagating across. It's kind of a idealized picture because there are lots of complications here. You can see actually this is an average, so you can see here that there is this detour of MJOs across here. Sometimes it crosses right over here, sometimes it seems to get stuck over here, sometimes it weakens and then re-strengthens on this side, but here it interacts with the Australian monsoon. But this also shows clearly how the active phase of MJO here is associated with the stronger jet stream over here, and then it crosses the Atlantic back into the Indian Ocean, Western Indian Ocean. The precipitation phase dies away because in the Eastern Pacific the temperatures are too cold, but the circulation patterns often remain and they go across. So not all MJOs circumnavigate, and some of the MJOs are supposed to reinvigorate on the Western Indian Ocean after crossing over, and some are called primary MJOs, which originate and are born again. Well, again, they are born, not again. And there is supposed to be extratropical perturbations which make genesis of the MJO possible, and so on. So the main thing to notice is that MJO convective phase, as it goes across, can have many effects. It can obviously provide clusters of convection, and it also affects the MJO phase also interacts with the easterly waves transitioning here across the Atlantic into the Eastern Pacific Ocean, where there is cyclogenesis, as we know. And of course it interacts, the easterly waves can come across all the way and interact with the monsoon trough, ITCZ, and the confluence zone that we had talked about here in the typhoon genesis region. This is the figure showing composite evolution of the 200 hectopascal velocity potential anomalies in 10 to the 5 meters squared per second, and points of origin of tropical systems that developed into hurricanes or typhoons. So you can see here we are looking at basically phasing with respect to the MJO convective and dry phases. So you have day 0 here, where there is dry phase over the maritime continent and the Western Pacific, and you can see that there is genesis here in the dry phase in day 0, but if you start date -15, the convective phase is here, and there is more systems that have been born and grown into typhoons or hurricane here, and also in the Eastern Pacific. So is there a systematic difference in the number of typhoons and hurricanes born based on the wet or dry phase of the MJO, and if so, what is the process? Does it affect cyclogenesis, favorable conditions in terms of, let's say, shear, vorticity, or there can also be convection that loads the moisture in above the boundary layer and produces a potential vorticity maximum in the lower level, which reduces the Rossby radius of deformation, which allows the incipient perturbation to grow, because if it is if the Rossby radius of deformation is smaller, then the perturbation has the chance to be larger than the Rossby radius and not get diffused away, as we remember the definition of the Rossby radius of deformation, right? So the actual mechanism of exactly how MJOs affect cyclogenesis is debated, and it isn't clear that the dry phases and the wet phases are working differently in terms of cyclogenesis versus the direct impact on the growth of the cyclone, for example. Okay, so basically lots of evidences of interactions between MJO phases and cyclogenesis, but no accepted theory as to exactly how it happens. But definitely the MJO phase affects the transition of the easterly waves into this region and cyclogenesis on this region, and active phase here and the cyclogenesis. But there are also some cyclones born in the suppressed phase of MJO, or the dry phase of MJO. This is another way to look at it. This is a work by Susana Camargo and Adam Sobel, the Columbia group. Here we are looking at genetic genesis potential. I will show how that is defined as and OLR anomaly composites. So they are deviations from the background genesis potential that is computed, and the phases 2 and 3, 4 and 5, 6, 7 and 8 back to 1 are considered here to show that the convective phase, so when you have let's make sure that the OLR phase is consistent. So OLR positive anomalies are shown in gray, which means it's the suppressed phase of MJO. This is the black lines, which are negative anomalies, which means it's the convective phase. So convective phase of MJO has higher genesis potential in each phase, okay, and the location differs. Indian Ocean into the maritime continent region. Over here there is also cyclones being born. Of course there are cyclones being born here, cyclones born here, and so on. And you can also see phase the different season. This is January, February, March, and this is October, September, August, September, October, and you can see again the relation between MJO phases and genesis potential. What is genesis potential? It is defined as this complicated expression here that depends on eta, the absolute vorticity at 850 hectopascal in 1 hour second. H is the relative humidity at 600 hectopascal mid-tropospheric level. Pi is the potential intensity in meter per second. You remember we defined that before. And vertical shear is the magnitude of the vertical wind shear between 850 and 200 hectopascal in meters per second. So that also confirms that there is a definite relation between MJO phases and genesis potential. So again, we can say that there is definitely a modulation of the cyclogenesis, and exact mechanism is not known, but there is a relation between phases of MJO and cyclogenesis, and also the systems, easterly waves coming into the eastern, northeastern Pacific, and MJO phases and cyclogenesis in that region. By the way, I should mention that the jet here and the relation with the MJO produces barotropic shear and can, as we know, put down energy that also can be favorable for cyclogenesis. That's why I had shown this and I forgot to mention it. But also we remember that the MJOs are associated with Kelvin waves and Rossby waves and Rossby gravity waves. So those waves are also associated with cyclogenesis. So the convective phase again can produce mesoscale convective systems, moisture loading, potential vorticity maximum, reduced Rossby radius of deformation, but also provide waves. For example, in the Indian Ocean, cyclones, specific cyclones are often done as case studies, and they are shown to be associated with favorable phases of MJO over the Indian Ocean. So all those processes matter, and I just added it because I had forgotten to mention that. Okay, just remember that. Let me add that I'm just adding stuff here, so I don't know if it's working or not. But the other thing we had talked about was the African Saharan air layer and its reversal of the gradient by the upper level heating and establishment of the African easterly jet and its extension into the cyclogenesis region and its potential impact on the easterly waves and so on. These are kind of processes that have correlations, but exact links are not always known. And the relation between West African rainfall at intraseasonal timescales and cyclogenesis are also speculated, but those relations are also not very well known. So there are potential links between Saharan air layer, African easterly jet, African easterly waves, and maybe also West Sahelian rainfall and intraseasonal modulation of cyclogenesis. So in that context, we should combine MJO intraseasonal activities and modulations of cyclogenesis and the Saharan air layer and Sahel rainfall as well. But all these are still to be fully explained process-wise. Okay, so we will leave it there.